Hi, my name is Nick Beesbruck. I'm one of the team members on Team 5 for Grand Valley State University's engineering capstones. Like I said, I'm on Team 5, and our goal was to build a radiation detector for our sponsor, BAMF. So the team, there was four of us, all engineering students. First, we have Jacob, who is a computer engineering student. He was the sponsor point of contact, so he was in contact with Paul Shields and other people at BAMF throughout the project. We have Matt. He is the only electrical engineering student. He was the faculty point of contact, and he was in contact with our main group advisors, which were Professor Zeidema the first semester and Dr. Rhodes the second semester. We have Ben, who is the also a computer engineering student. He was the team lead. And then finally, like I said before, my name is Nick. I'm a computer engineering student, and I was the secretary of the team. So BAMF stands for Bold Action Medical Future. BAMF's goal is to achieve intelligence-based precision medicine through AI-enabled molecular imaging and theranostics, MTRT. They specifically use theranostics to treat cancer patients, which leads us into the objective of the project. The objective of this project was to build a network-based radiation detector that will be used to give BAMF gamma radiation readings from wherever each detector is deployed throughout BAMF's radiopharmacy and facilities. So why make a new radiation detector? The current radiation detectors used by BAMF are outdated and have no network connectivity. There hasn't been really any breakthroughs in network-based radiation detectors and radiation detectors in general, so this was a good opportunity for BAMF to pioneer new and more robust radiation detectors to be used for MTRT. So the new detector, the product BAMF requested, involves the integration of a Geiger-Mueller tube with a networkable microcontroller to measure gamma radiation. The product must be able to be deployed around their facility to relay live radiation values to a custom web server designed by another team at Grand Valley. The key specifications for this project is that we need a high bias power supply to power the GM tube to be able to detect radiation pulses, and then we need data encryption and transmission to that custom web server. So BAMF wants to be able to take that data, encrypt it, and send it to their web server to be able to read and parse the data from wherever they please. Our new detector needs to have an Ethernet connection to be able to send this encrypted data to the web server, and since we're using Ethernet, power over Ethernet is a good option to power the system, as it provides higher wattage and uses one less connector on the system. And then finally, also a warning system needs to be on this so that wherever each detector is deployed, BAMF employees, patients, and nurses can know when there's higher than usual radiation in the area. And then finally, this unit needs to have protective housing so that it can be easily deployed wherever BAMF would like it to be deployed. So for concept selection, there are four main concepts for sections of the board we had to work with. First one was coming up with an MCU with network capabilities. Next was a high bias power supply to again be able to bias that GM tube to detect pulses. We decided to go with an audible alert system so that BAMF employees, nurses, and patients can all know when there's higher than usual radiation based on a loud, obnoxious beep. And then finally, we also had to look in the enclosure to decide how to make it cheap, robust, and simple to produce, but also to make it so whether it's deployed on the ceiling, the wall, underneath the patient's bed, underneath the chair, a cabinet, wherever BAMF wants to deploy it, it needs to be robust so that it needs to be robust. Concept selection. The main components we decided after the concept selection was to use the Esp32 as the MCU. This is a very powerful MCU that has Ethernet and Wi-Fi capabilities, so checks two boxes in regards to BAMF wanting to having network capabilities. We're using the A2OP-5 high bias power supply to be able to provide a high enough bias voltage to the GM tube. This linear power supply can supply up to 2000 volts, which is perfect for biasing a GM tube. We went with the CVS1508 buzzer. It's a very simple and robust buzzer that provides a great volume and frequency range to provide audible alerts. And then we decided to go with a 3D printed enclosure, which is easy to produce, cheap, and allows for maximum customizability if BAMF wants to make any changes in the future. So going deeper into the concept selection, the Esp32 Mcu Development Kit, which is pictured to the right, has UART, PoE, Ethernet PHY, and then the ESP MCU itself has Wi-Fi capabilities, which are all good options that need to also be added to BAMF's radiation detector to allow for programming, easy communication, and network connectivity. So after going through the concept selection and figuring what we needed to do, we had to come up with a proof of concept, which the Esp32 Mcu Development Kit has, like I said earlier, provides lots of good features for the system, but we also had to make a prototype PCB with a flash, buzzer, and a high bias power supply for that GM tube. Specifically for flash, we decided to use the SD card. And so after creating this prototype board and hooking it up in conjunction with the ESP development kit, it provided us a good idea of what changes needed to be made for the final board, and also helped us prove that our concept was feasible. So the final product is a custom PCB that includes Geiger-Muller tube integration. It has a high bias supply for the GM tube to be able to bias the GM tube and get good radiation data. This board has Ethernet and Wi-Fi capabilities, Ethernet through the PHY chip and Wi-Fi through the EMC or ESP32 microcontroller. So BAMF has lots of options for network capabilities with this. We're using power over Ethernet to power the system, since we already have the RJ45 on there for the network connection. We use UART as communication and the programming line. So UART provides lots of good debugging options for BAMF when deploying these. We have an audible alert system through that CVS 1508, which again is a loud and robust buzzer to alert patients, nurses, and other BAMF employees of higher than usual radiation detected. And then as in the top picture, we have a custom enclosure which secures the board, or secures the PCB into the enclosure, and then also allows that enclosure to be mounted wherever BAMF would like to deploy it. So after working on this project for the last two semesters, 8 months, we came up with some what's next for BAMF. BAMF has a few options on where to improve and add some more features to this project. So the Esp32, like I've said before, has built-in Wi-Fi capabilities. So additional software can easily be written for that. So BAMF can have units run on Wi-Fi. They can have units run on Ethernet, but they could also use both, with Ethernet being a failsafe just in case the Wi-Fi goes out. So in regards to encryption, we use the libcurl encryption library, which is a very powerful library, but it unfortunately was very hard to integrate with the Esp32. So software modifications to the web server and the radiation detector, using either making libcurl more robust or finding a different encryption library would be helpful to simplify future revision changes. And lastly, we said BAMF could also use a dual MCU setup. So use the Esp32 as a Wi-Fi chip and also control maybe some other peripherals, whatever they would want to use it for, and then having another regular MCU to control most of the other features and peripherals. Thank you for watching.